We've all seen it in the news, right? Those unbelievable images of cities just flattened. But what is an earthquake really? I mean, we feel it right here on the surface, but the real story, the one that matters, starts miles and miles beneath our feet, where these incredible forces are constantly battling it out. So let's dig in. Think about it. It can start as this low, deep rumble, and then it just erupts into pure violence. Back in 2008, a massive 7.9 magnitude quake just tore through China's Sichuan province. Buildings didn't just crack, they collapsed like they were made of dust. Or maybe you remember 2004, a truly colossal 9.2 quake off the coast of Sumatra. Now that one didn't just shake the ground. No, it literally moved the ocean, unleashing a tsunami that would change lives forever across Southeast Asia. And even in a place like Japan, which is, famous for its earthquake preparedness, the Fukushima quake was just this devastating reminder of the raw power of our planet. But here's the most important thing to get. These are not random acts of chaos. Not at all. They are the predictable, inevitable results of gigantic forces that are always at work. So what is actually happening when the very ground beneath us starts to feel like it's turning to liquid? At its heart, an earthquake is just a sudden, rapid release of energy. Way down inside the Earth, at a point they call the focus, the rock just can't take the strain anymore. It gives way, and all that pent-up energy explodes outward in every direction. And that energy travels in the form of powerful seismic waves. Okay, so to really get a handle on that energy release, we've got to look at the structures that are storing it up in the first place. You see, the Earth's crust isn't one solid piece. It's actually broken up into these massive tectonic plates that are always on the move. And where they meet, where they grind and scrape against each other, they create these huge fractures we call faults. That's the real action zone. You've probably heard of the most famous one, the San Andreas Fault in California. That's a perfect example. So, how does all that tension build up? Well, there's this fantastic idea called the elastic rebound theory. The best way to think about it is to imagine you're trying to bend a really thick stick. As you apply force, the wood starts to bend and deform, right? It's storing energy. You keep pushing and pushing and pushing until finally, snap. The stick breaks and violently springs back. That snap, that's the earthquake. The rocks along a fault are doing the exact same thing, just on a scale that is almost impossible to imagine. Okay, so the rock has snapped back. Now let's track how that sudden burst of energy actually travels. That energy races through the Earth's interior in two main types of waves. The first to show up are the P waves, or primary waves. They're the fastest. They compress and expand the rock, kind of like a slinky being pushed and pulled. Hot on their heels are the S waves, or secondary waves. These shake the ground up and down or side to side, like snapping a rope. But here's the really cool part. S waves can't travel through liquid. By tracking where they just disappear inside the planet, scientists figured out something amazing. The Earth has a liquid outer core. That discovery was a total game changer. And finally, you get the surface waves. As their name suggests, they travel along the crust. Now, they're the slowest of the bunch, but believe me, they're the ones that cause the most destruction. They have this complex, rolling motion that is just absolutely brutal on buildings. We can all feel these waves, but how do scientists actually measure them and turn all that shaking into useful data? So how do we record all this? We use a tool called a seismograph. It's actually a pretty clever concept. Imagine a pen hanging from a spring over a roll of paper. When an earthquake hits, the whole machine shakes with the ground, but the pen, because of inertia, wants to stay still. So as the paper moves under it, the pen draws out those squiggly lines we've all seen. That record of the Earth's shaking is called a seismogram. Okay, this is a really crucial point because people mix these up all the time. There are two totally different ways to measure an earthquake's size. First, you have magnitude. That's a single number that measures the total energy released way down at the source, at the focus. Then you have intensity. Intensity describes the effect of the shaking at a specific place on the surface. So a single earthquake has only one magnitude, but it can have many different intensity values depending on how far you are from the center and what the ground is like where you are. So why is this number so important? It's because the Richter scale is logarithmic, which is a fancy way of saying it grows incredibly fast. This means a magnitude 6 earthquake isn't just a little bit stronger than a 5. No way. It releases about 32 times more energy. It's an absolutely massive leap in destructive power. And, the initial shaking from the quake is often just the beginning. The effects that come after can be just as deadly, if not more so.
One of the most terrifying things that can happen is something called soil liquefaction. Basically, if the ground is saturated with water, the intense shaking can turn solid earth into something like quicksand. And when the ground beneath them basically turns to soup, entire buildings can just tilt, sink, or collapse.
It's an incredible image, isn't it? The soil's internal structure just gives way. As the source says, the clay particles collapse like a house of cards. The very ground you're standing on loses all its strength. We've seen these shocking pictures from places like Japan and Alaska, where entire apartment buildings are left leaning at these impossible angles. Now, when a major earthquake happens under the ocean, a whole other nightmare can begin, a tsunami. And it's so important to get this right. These are not tidal waves. They have absolutely nothing to do with tides. They are seismic sea waves, caused when a fault on the ocean floor suddenly shoves a massive column of water straight up. And here's how it unfolds. Out in the deep ocean, that wave can be traveling as fast as a jet airliner, but it might only be a few feet high. You'd never even notice it. But as it screams towards the coast and hits shallower water, the wave slows down, and all that forward momentum has to go somewhere, so it goes up, piling the water into a towering, terrifying wall of destruction.
So, we understand what causes them and we know how to measure them, but the ultimate goal, the thing we all want to know, is can we see them coming?
And again, we've got to be super precise with our words here. Short-range prediction, saying a magnitude 7 will hit Los Angeles next Tuesday at 2 p.m. That's the holy grail of seismology, but right now we simply cannot do it. There's no reliable method. What we can do, though, is make long-range forecasts. By studying fault lines and historical records, scientists can figure out the probability of a major quake hitting a region over, say, the next 30 to 100 years. And that is absolutely vital for things like building codes and city planning. So this leaves us with this incredible challenge, doesn't it? We live on a planet that is constantly moving, constantly alive. We can't stop the earthquakes, and we can't, at least not yet, predict them with any short-term accuracy. So the real question isn't, how do we stop them? It's how do we live with them? How do we build our cities and prepare ourselves to be resilient in the face of the Earth's inevitable and truly awesome power?